So time for resuming our understanding of naive Bayes. So how many of you think so far that you understand naive Bayes? How many of you have no idea what naive Bayes is? Okay, some idea. That's good. So today we are going to talk about how we are going to do, we have already talked about this, but we will kind of resume and do some recap on naive Bayes, especially in terms of text classification. And in the last class, we actually said that naive Bayes makes this assumption that every random variable that we use to model the data point are independent of each other. And that's why you could do multiplication of individual probabilities to estimate the joint probability, right? Now, when it comes to text, what is actually text? Text is basically a what?
Binary value.
Is text a binary value?
Behind the scenes, I guess,
A lot of binary values.
or ASCII values.
ASCII values. Okay? What are they? Combination of digits. Does it have to be a digit?
Well, by digit, I mean just any
Character. Combination of character. Okay? What else? What is text? Yes.
It's a code, there's like a syntax.
It's a syntax. Okay? What else? A sequence. Okay? Good. Yeah, all of them are true. So essentially, when we think of this text, like there is a text, we have a document, it's just a sequence of words we write, right? It's a sequence of characters as well. We could visualize this in terms of whether a particular word is present in the document or not. We could do many, many different things, but essentially it's a collection of words in a particular sequence, right? So now the question is, how do I represent this text, right? What is ideally, our text is a sequence of characters and especially words, because words have the most intuitive semantic meaning to us, and a set of words, if we stitch together, becomes a sentence and conveys some meaning. Now, what is the best representation for a document? That is the document itself, right? If you just write the entire document, that's the best representation we have. But what is the problem with that? Yes. Inconsistent size. What else? They are all going to be unique, right? So this representation is not helpful, because when we talk about representation, we want something common, a common general representation of something. If we just represent this document by itself, then every document is unique. You need separate representation for everyone. So what can be a more common one? So one way we discuss this is assume that each position is a random variable, right? We could make that assumption. So we could represent this document by saying it's a collection of random variables, and for each position I, we have a random variable, and the random variable could take the value of what? What values this random variable could take? Yes?
Any word from the vocabulary?
Any word from the vocabulary, right? Because these are words that we sample from our vocabulary, right? These are the possible values each random variable could take. Now, if we don't do naive Bayes, let's say, if we don't do naive Bayes, but we want to know what is the probability that the word W10 is going to be baseball, let's say. This is X10. So yes.
If you don't look at the rest of the document, then it's just 1 over the size of the vocabulary.
The probability.
Yeah.
Yes, I understand, but we are not making assumptions yet, right? The point is whether this word 10 is going to be baseball. Ideally, depends on what? Depends on what? Context. What is the definition of context?
What you're surrounded in.
How far?
For a word, it would be like the words that it's surrounded with and the context of the document.
Surrounded how far? What is your definition of context? Yes.
Well, what you're getting at, like, you could just do the words before and after, or the 2 words after, the 2 words before, 3 words, and that's a choice you have to make. Or you do the whole document.
Why not the whole document?
It might just be too intensive to do the whole document.
But ideally, I mean, if you do some creative writing, I mean, this what could even depend on this one. Depends on how you write. So W10, like X10 can depend on any word, ideally. It might connect to some ideas. Maybe you are talking about a person here, maybe that's Trump. Or should I replace with Biden? It doesn't matter. And maybe this is the same person that is being referred to. So if these 2 words are representing the same person, so they are connected, even if they are far away. Right? So now the question is, if I don't make any assumption, then any word in a document will actually be connected or be correlated with other words. That's how the real world works. But let me switch the problem. Let me switch now, saying we don't have the whole document, but we are writing a document, correct, right now. And we have written up to this W9. We are still writing it. It's not complete. Now tell me this W10, I mean the X10, what should be W10? What does it depend on?
The words from W1 to W9.
The words from W1 to W9, whatever you have written so far, right? How many of you have heard this name, LLM? What does it mean?
Large language model.
Large language model, right? Forget this large. The main part is language modeling. And you know what? Language modeling is what this means. What is the probability that X10 will be equals to W10 given W1 to W9? This is language model. This is GPT. This is Llama. This is Alpaca. This is Google Bard.
They use the Bayes, naive Bayes.
They don't. They model this probability. But yes, I mean, what we are going to do in naive Bayes, they don't do that. But essentially, naive Bayes is one way to estimate this probability. But they have a better way to do this probability. That's all language modeling is about. You are just predicting the next word. Okay? But again, this is not part of this course. We have a graduate level course for natural language processing where we go into depth about this one. But here, the point is, so this probability of W10 given the context, and the context should ideally be W1 to W9, right? Is actually what this equals to is probability that you see W10 and W9 given the chain rule, right? W1 to W8. The probability that you see W9, W1 to 8. So given that you have W1 to 8, you have CW9, and so given that this, you are seeing this, right? So now you could apply this chain rule, and that basically means you need to estimate all these probabilities if you don't make an assumption for naive Bayes. So what naive Bayes does is it basically says, you know what? Probability of W10 is essentially equal to this. It does not depend on what you have seen so far. Or even if the whole document is given, it doesn't depend on what you are going to see in the future. Okay? So first of all, is that a good model?
For this example, no.
No, right? I mean,
Well, it could work.
what?
It could work.
It could work. Why?
You could get something useful out of it. Like it might not be perfect, but you could get something that's useful.
Yes. I mean, that's why we are starting this. It is useful, but the point is it's very dumb. I mean, if you think about what it is modeling, it is basically saying this word that you see here has nothing to do with what you have seen here and what you have seen here. Right? Then think about now, but why do we want to use such a dumb model? That's the question, right? Because if we don't use that, then think about how many parameters you need to estimate. Let's say our entire document is a single representation. Then how many probabilities we need to estimate? So here, assume that our vocabulary size is 10,000. That is the size of the vocabulary, 10,000. And let's say our length of the document is 1,000, for example. So you have 1, 2 till x 1,000. Right? Now, if I don't do naive Bayes, I have to estimate a probability for each possible document that is 100 length long. Let's say that's our maximum limit. Okay? So, how many probabilities do I need to estimate? If I don't do naive Bayes, if I just want to represent all possible combinations of documents. 10,000 to the power 1,000. Why? Because how many options you have to fill this position?
10,000 options.
10,000. How many here?
10,000.
10,000. So you are essentially multiplying 10,000
1,000 times.
1,000 times. So if you want to estimate all the probabilities that you need to model this sequence, is this number. That's just the number you need to estimate. Forget about the question how you are going to estimate this, because this is most likely a unique document. You are not going to see more than one example of this. And for most of the possible sequences, you will never see an example, because we are not even considering sentence structure, syntax, grammar, anything. A lot of documents will just be garbage. Right? Okay, what is a better thing we can do? The naive-Bayes assumption. That is too simplistic. And yes, the language models that you hear about today, GPTs and all that, they do a better job at this. They are not so dumb. But in the extreme, this should be our ideal probability to calculate, but we cannot do this because this is not feasible. So the simplest thing you can do is to assume that each position is independent. So whatever you see here, that is the naive-Bayes assumption, right? Whatever happens to your random variable here, the other random variables don't affect it. What does that mean? That means what is happening for W1, you don't really need to care about the rest. So how many options for W1? How many?
10,000.
Just 10,000. Right? How many for this one? Again 10,000. But you are considering them separately, so that multiplication there now becomes just an addition. You see? You are just adding this 10,000 times, which is essentially
10,000 into
10,000 times 1,000. Much better than this. Right? But the question is, can we do better? Do we really need to estimate this many? Because for each position, we are estimating a probability over all the words for each position. Yes?
Some words are going to be more useful, so you could scan the document and find the repeating words, and then base your algorithm off those.
So for the important words, what should we do?
So you could develop a heuristic where you scan the document and you find the words that are repeated the most. Those
Yeah.
might be more useful, and then
Okay.
you just calculate those probably.
I see, yes. That's even one step further, but even before that, finding important words, we could always discuss some less important words or like very rare words. That is definitely one thing. We could shrink this size, 10,000 to maybe 1,000 by just selecting the top most 1,000 important words, frequent words. That is something we can do, but even before that, think about this. If a particular position K does not depend on the other positions, so do I need to estimate a probability distribution for this position and this position separately or not? I mean, does that really happen? Or the question is, if we are making this assumption that the other words don't affect a particular word, can we say, is it useful to say, like, in the third position, I will see Trump with a probability of 0.6, but in the 10th position, Trump will have a probability of 0.4. I mean, ideally it might make sense, but if we make the assumption that this Trump and this Trump, none of them are affected by the other words, in that assumption, do we really need to make them different? Does that really add much?
So is that different? Likelihood of it being in a certain position versus likelihood that it's surrounded by other words?
Yes. Yeah. So there are two different things happening here. That's what you need to understand. One is a word is affected by other words, and then a particular word is affected by its position. These are two different things.
That's still a large number of calculations, right?
Yes, but if you assume that the position does not make a difference for a particular word, if you make this assumption, furthermore assumption, first assumption is no other words affect a particular word. The second assumption is for one particular word, wherever it is within the document, it doesn't make a difference. It's not a right assumption to make, but if we make it, for each word in say, each position, right? So we are essentially assuming in each position, for each word, the probabilities are same. After making all these strong assumptions and unrealistic assumptions, dumb assumptions, the model that we get is called bag of words. Essentially, you are packing things in a bag with some counts. So, tell me, if I do bag of word, that means the position doesn't matter. Then how many do I need to compute probabilities?
10,000.
How many?
10,000.
10 or 1? 10,000, right? Because 1,000 is the position, and the position doesn't matter. So for each position, it's the same probability. So you just calculate one probability distribution. So that's just 10,000 numbers. And then you can go to his suggestion, like I don't want to compute 10,000 because I don't care about rare words. I just want to look at the frequent top 1,000 words. So that is the number of probability that you want to compute. That is really feasible, right? Just computing like 1,000 numbers, that's not bad for a computer. That's what you do with Naive for text representation with the two assumptions. The basic Naive assumption is no other words affect a particular word, and the additional assumption that we make for bag of word is position also doesn't make a difference for the probability of sampling a particular word. This is called the bag of word model. This is called words model. It is called the unigram language model. So whatever large language models you see is just a better language model today, like GPT, Bird, Llama, everything. But everything starts from here, the unigram language model. That's the basic, most basic language model you can create, the bag of words. Okay? So now we have shrink down from 10,000 to the power 1,000 to 10,000 times 1,000 to 10,000 to even 1,000. And the good part is, still for some task, these models do pretty well. These bag of word models.
Can you give an example? Type of task?
Okay, so think about similarity between two documents. So you have a query queue. So first of all, let's think about what should be the, so this is a representation essentially for a text document, right? So how does bag of word look like? So if I tell you, I have a document, D1, which is going to be a collection of words, right? How do I represent it?
A is in W1 probably. Most common first, right?
I mean, tell me like in terms of number, it should be a vector, right? What are the individual row, like cells of this vector? Numbers. In a bag of word representation, what does this cell means?
Is that a word or?
Count of that word.
Oh, right. Is the row the words and then the?
Number of? But which word is this?
Most common?
The first word.
It doesn't matter. I mean, you just need to have a mapping of all the words in the vocabulary, right? WK. Right? I mean, if it is N, then it's N. That's your vocabulary size. You just need to have the counts, like this word appear twice, once, 0, 1, 3, like this. That is your bag of word representation. But now, if you have a document like this and a query like this, another let's say small word collection, you can create another vector for the query, because that is also a document, right? It's also a text document. So you can also create another vector representation. Maybe it will have more zeros because it's shorter. But still that is again a vector. Now you can do dot product of this vector. You could do similarities of this vector to actually find out the similarity of D1 and Q1. And based on that, you could do search. That essentially brings out documents that are close to Q1. And essentially that's the most basic search algorithm you can implement with this kind of models. It may not be very good, but still sometimes it does reasonably well.
The size of the vectors are the same?
Yes, because it's a vector of dimension of the entire vocabulary for all of them. And we'll go into this representation. So first of all, when we made an assumption, right? When we made the assumption that surrounding words does not make a difference for a particular word, then we could replace the entire sequence of the probabilities for each word in the document, like the whole document, by a multiplication of individual words. Right? So tell me here, if it's a text classification problem, right? What do we mean by text classification? What are we classifying text into? That's the question, right? And we have shown example previously, like it could be, if it's an email document, it could be spam, not spam. That could be a label. It could be the topics, whether it belongs to sports, whether it belongs to politics or to some other topic. It could be topic based, right? So that depends. Your labels could be any discrete labels. But as long as you have a label Y, what you are essentially trying to do is, for a particular topic, what is the probability that you will see a particular word in the document? That's what you are trying to model. But instead of modeling the whole sequence, you just model one word, because you have made the naive Bayes assumption. Any question on this so far? And by making this assumption from this model, we come to this number of probabilities, right? But then we can simplify further. We can say position also doesn't matter. When we say position doesn't matter, so that essentially boils down to this model. What is the difference between the previous model and this model? Because now you are saying probability of xi, it doesn't depend on I. Right? This I is the position from 1 to 1000. So probability of xi, this I, you don't need to consider this when you make the bag of word assumption. So you just need to infer 10,000 probabilities. Even better. So what it essentially means for a bag of word model, a text like this, when the lecture is over, remember to take your bag, is the same thing for the algorithm as saying bag is lecture over, remember take the to when here. Bag of word will treat both documents in the same way. It's just a bag of words. I mean, if you compute a bag of word representation from this and this, you will get essentially the same values. Right? And the other part is the representation of this vector. So remember, when I said bag of word vector is a vector over the entire vocabulary. It's not a vector over the length of the document. What is wrong if I use the length of the document here instead of, this is not WN, rather this is WL? What is wrong? What is the problem?
It'd have to be unique words in the document, like you'd have repeat words in your vector. Or it wouldn't match the number of vocabulary size.
It will be unique for each document and the vector size.
Right. The main problem is, if you use this index, these vectors will be of different size. Think about this, right? A document is 100 words long versus 1,000 word long. These two vectors will be very different size. Then how do you compare these two vectors is a challenge. Because all you are doing in order to come up with this representation is to compute or compare these different documents, right? But if you have to come up with different representation, that's not a general representation. So that's why instead of using the length, you want to use the unique words in the vocabulary. That is constant for all documents. Because if you have a fixed vocabulary, these are your words in English language, let's say, then that doesn't change unless you coin a new term. And then your vocabulary, of course, changes. But then that's a whole other story how to deal with that. But assuming that vocabulary size is fixed, then your representation doesn't change. Is that clear?
If you have a small amount of words, will that not work very well?
If I have a small amount of words for a document or the vocabulary?
So like if you have a language that only had like 20 words,
Yes.
that would not work then, would it?
Why not?
Because it would be very hard to classify based on probabilities.
Well, if you have a language that has only 20 words, you will not be able to express a lot of things even, right?
That's not true. You can, if you had 20, say 20 options at every position, and you had infinite positions, you could express infinite words.
You are then not talking about words, you are talking about characters.
Yeah.
Yeah. So characters are not words. The assumption here is words,
Okay.
right? Because different sequence of characters can frame different words, and that frames different, but word is a semantic unit. Characters don't have a semantic unit. So the probability that we saw, we do a multiplication of I equals to 1 to the length, let's say L. And we compute the probabilities for each position given some particular topic, let's say, right? Now we said the position, for a particular position, it doesn't make a difference. It doesn't make a difference, right? So how can we revise this? Because this is going over an index of over the position. So that's why the I is still here. Although I will not make a change for W, but we still are iterating over this. We multiply this multiple times. But the point is, if I want this representation, instead of L, I want the vocabulary, how this formula should change. What should be the index now?
B.
What should be the index? Right now we are multiplying over all the positions here. But instead of that, we want to iterate over
Everything with vocabulary.
everything in the vocabulary, right? Everything in the vocabulary. So then your index becomes everything in the vocabulary, and for each word in the vocabulary, now it's not a position, it's now a unique word in the vocabulary. But what is the problem here? If I switch it, is that okay? Right now, does the equation look okay? Or do we need to take care of something else?
Wouldn't you have a lot of zeros in there though?
Yes, you will. And then you want to take care of that using that trick, the smoothing trick. You don't want to make naive Bayes go to 0. You will force everything to be non-zero. But the problem here is I mean, that's the basic problem with multiplication. But can I just replace L with V and are we good? Yes.
So WI is the count of the ith word in the vocabulary, right?
WI is the word itself, it's not the count. What is the probability that you will see this word?
When you see every word at least once.
Isn't that equal to just 1?
So, think about this. When you come over indexes, can a word be repeated?
Yep.
So, it's most likely you are going to have a probability of go, and again, somewhere here you also have this word go. You are multiplying the probability of word go twice. Right? But if I go over all the words in the vocabulary that are unique, does that handle the frequency?
Yes.
So what we need to do in order to model that frequency?
Maybe sum the repetitions.
So we need to account for that repetition.
repetitions.
So if this word is appearing thrice, so that particular word probability should be multiplied thrice. Essentially, you want to put a power of Wi inside D. How many times it appeared? Because now, previously, you were allowing repetition when you were going over the index of the length of the document. But right now, even though this is a even higher dimensional vector, each of the words are unique now. So in order to account for multiple occurrences of a word, you need to multiply their probabilities by the number of times they appear. Is that clear? So that's why the previous equation you see here, this one, actually changes and becomes something like this. You see the I is gone, right? It doesn't depend on a particular position. But you need to account for the number of times the word appears. Because each word is unique, and you are not considering the frequency if you just multiply just once. But why do we do this from here to here? Again, why don't we do this? And why we want to move here? What is the benefit? What is the benefit?
One is the same vector length.
Same vector length, right? Same representation. General representation for all document. If I have two different documents here, I need to do a multiplication over two different lengths with this representation. But if I have any different lengths of documents, the number of multiplication you will do is essentially the same. The terms. The vectors will be of the same size. Is that clear? Yes.
Is that better than taking like a set sample size? Say you sample words from documents? You could take the same sample size of every document and then it would be the same size vector.
You are sampling essentially words, right?
Yeah.
But there is no guarantee which words will be sampled. It could be any word from the vocabulary. Then if you are sampling, you are essentially saying a 10,000 word document. From that, if I sample 1,000 words, and I have another 1,000 word document, right? So you are, if you sample, if you downsample from the larger document, you are essentially creating two identical size documents. That is correct. That is another way to do it. That will just depend on how well your sampling is with respect to your original document. Because sometimes if you do uniform sampling, you are essentially sampling over a big chunk, but maybe the essential information is at the last paragraph. And you don't really know which document, how to sample from that document. You might break the properties or the useful features of the document through the sampling process, because sampling is always destroying information, right? It's kind of extracting limited information. Yes, but yeah, that would solve this problem. All right. So bag of word essentially comes to a representation like this, vector, where you just count the number of words that are there. But we are talking about this probability, right? How do we compute probability from these numbers? If I give you the counts, frequency counts, how do I convert that into probabilities for each word? Ideas?
Could normalize it.
Or the summation of all the counts?
Exactly, the relative frequency, right? The relative frequency, the number of times you see the word appearing divided by the length of the document. Because if you add those counts, that will be equal to the length of the document, right? But what is the problem with this? There is always a problem. What is the problem with this? If I compute this probability and do the multiplication, what is the problem? It will be small, or it will be?
Close to 0.
It will be just 0, because at least some of the words will be missing. There is no document in the world that contains all the word in the vocabulary. Right? How do you handle that?
Add one.
Eliminating.
smooth it.
Yes, do the smoothing. Add 1 plus what?
One. Okay. Yeah.
What is k?
Some constant.
What is that constant?
The vocabulary size.
Vocabulary size, because you add 1 for each word in the vocabulary. Right? There are definitely better smoothing methods, but this is one dumb one that works. Okay, so coming back, yes.
We reduce the size of our dictionary, like from 10,000 to 1,000, and so there's some words that are in our document which is not in the dictionary, some rare words. So there shouldn't be the length of the document itself.
So the assumption here is whatever is not in the document, no word is appearing in the document that is not in the vocabulary. That is the assumption. Your vocabulary encompasses all the words. That's the assumption. So in real life, when this happens, how we handle this is just ignore that word. That is out of vocabulary. So you basically create a symbol called out of vocabulary and replace every word in your vocabulary, like whatever word are rare, with this token, and just make this one part of your vocabulary. That solves your problem. Now you know every word. Whatever is rare, unseen, just make it out of vocabulary. Yes?
Wouldn't this classify like two documents that have like say the same amount of like instances of B? Like it would classify those as the same comparatively, like if you had a document that had like a more important like noun but less times, like wouldn't that classify it incorrectly? Like it would link the two that have the same amount of these closer than just the one that has like no these, but it has the same like noun that's actually the topic of the document, right?
If, first of all, essentially if two vectors look essentially the same, but it could mean two different documents. Is that correct? Because you are just counting how many times the words are appearing. You are not considering where they actually appeared. It is entirely possible two different documents essentially giving you the same bag of word representation, right? Because you are just counting how many times "the" appeared, how many times "apple" appeared, how many times this appeared. In what order, in what context, you have not. You don't mention that. And it is entirely possible that two vectors will be almost similar or even identical, even they are very different documents. So in those cases, those two documents probably should be classified differently, but for bag of word, it will classify them because it has just one representation. It will classify them into one of them. The other one will be wrong, and that's why bag of word model doesn't work always. And that's why you need to consider the sequence, right? As a human, when you read a document, you kind of go through the document, you read, you kind of absorb the sequence. There is a semantic, that picture that you build on your mind. There is a lot of complex cognitive process that goes on. So the transformers, although it doesn't really simulate our human brain, seems to capture a lot of those semantic properties. And that's why those models are so popular now. They're so powerful. And today we don't understand how they make it possible. Okay? So, for example, if there is a famous classic dataset called 20 news group dataset. So it basically has 20 different news groups that belongs to, for example, some topics are related to graphics, hardware, autos, motorcycles, and all that. And if you try to classify using the bag of word, it looks like it achieves 89% accuracy. Pretty impressive, right? Because the actual probability you are computing is not very important. It's important to compare two different probabilities for two different classes and then assign the most likely one. That's why this is so powerful, because the comparison is important. The relative values are important rather than the absolute values. Okay? So all you need to know whether space is more likely than gun. You don't really need to know what is the actual probability of space, right? In order to do the classification. That's why Naive works pretty well. But not for every task. For simple text classification, it works pretty well. Okay, so far we have been talking about, and this is just a typical learning curve, like as you increase the training data set, the accuracy improves. So this is just a demonstration of your learning curve. But the point is, so far we have been talking about discrete variables when we talked about text. Why is that discrete? Why our x, all the x we talked about are discrete. Why is that?
Different words.
It's just a fixed set of vocabulary words, right? Our vocabulary size is finite. But now let's talk about continuous variables and how do we model that with Naive Bayes, because we also want to model the continuous variables as well. For example, images. If you want to classify an image, all you have is pixel values, right? And pixel values are continuous variables. Well, you could even assume that they're discrete, like from 1 to 225. That's not a 255. That's not a really a good model because they are not really labels. There is an ordinal value. Because 255 means entirely white, 0 means entirely black. The order also has some meaning there. If you treat them as individual labels, that's not the right way to do it. So it is continuous. So now, what do you need to do? You cannot estimate individual label probabilities. But you now need to, because you have a continuous variable, you need a distribution to estimate. Right? Because in the discrete case, why did we say like we have, for the distribution of word, we had 10,000 different probabilities. Why? Because this 10,000 word probabilities defines the distribution. That's the discrete random variable distribution, right? But now you have a continuous variable, so you need a continuous random variable distribution to consider. And turns out for black and white image, the Gaussian distribution is a good approximation to make. So what you want to do is each pixel, now instead in the text your feature was first each position, right? Each position was your feature. But then we changed the feature to what? Each word in the vocabulary, right? That is your random variable. But in case of image, what should be your random variable? Think about a general representation that works. Assume that you can rescale images. You want a general representation for an image. What would that look like? Yes.
Would it be all the different pixel values?
Okay. Yeah. So let's say you have a general representation of 8 by 8 pixels of images. Okay. That means how many pixels you have in total?
64.
64. So you essentially have 64 random variables. Use x64. Right? You just need to assign each pixel a value and you will get an image. For example, for text, you need to assign a word to each position. For image, you just need to assign a pixel value. Right? Okay. So, and the pixel values, let's say this is my 8 by 8 matrix. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? So now each is a pixel, and you need to know for each class how this pixel should look like. So let's think about a classification problem in text. How about numbers? Let's say I have some handwritten digits I want to classify. Okay? So here is an example. 1, 2, 3. I have written with my hand. Now you take a camera, you take a photo. You rescale it to 8 by 8 pixel images. Okay? Now you have many examples of me writing these digits. I write 1 multiple times with different slight variations, right? 2. Like this. So you take many examples like this and you create a training data set. Say, like, this is 2 actually. This is a class 1. This is a class 2. This is a class 3. So now our goal is to look at an image and determine what the actual digit is, because we are dealing with an image, not actually a number, right? Computer doesn't understand images directly. It only understands numbers. So that is the task. Now, let's say I'm given a training data set of many different handwritten characters and with the labels. And then the goal is to learn a classifier that will classify a new image into the right digit. That is our task. And we can use Naive Bayes to solve this problem. How? So you need to, for Naive Bayes, you need to understand what is the probability that y equals to 1 given a particular image. Right? What is the probability that y equals to 2 given that image? And you need to compute all the probabilities. Y equals to 9 given image and even 0. Right?
So for this one, you're just counting when that index shows up or when that cell shows up for the number, right? The probability that that cell will show up.
Yes. Yeah, I'm getting there. So the point is, you need to compute these probabilities, and whichever is higher, you will say, okay, this image looks like a 9. This image looks like a 5. But in order to do this, let's look at one of them. What we need to first know. How do I know? If I apply Bayes, what happens here? If I apply Bayes, how does this change? Come on, this is the basic Bayes theorem. A given B. What is that?
P of A,
P of
Y
image
into
given y equals to 1 divided by
P of Y
probability of what? Image. And here there is one more term. What is that? Probability of
Y equal
y equals to 1. Right. So, how do I estimate probability of y equals to 1 from the training data set I am given?
Count the number of ones.
Count the number of ones that are provided in my training set. Right? That is the prior probability of being 1. We can easily do that, right? Just count how many images you are given. Let's say you are given 10,000 images. Out of them, 2,000 is just 1. So 2,000 by 10,000 is your probability of y being 1 without any further information. That is the prior. Right? So from the training data set, we can estimate this. How do we estimate this from the training data set? What does this mean actually? Now think about this whole image. And this whole image is what? Is a collection of what? Pixels. And if I assume that all pixels are related to each other, if we don't make an independence assumption, that means you need to model the entire set of 64 pixels. That blows up. But then we are going to do this trick, right? We are not going to blow it up. Are we out of time? No, we are not. So, we are assuming each of the 64 pixels are independent. That means this image is essentially what? A multiplication over the pixels for all the images that has a label 1. For each pixel. What this basically means, let's say I'm talking about this pixel, and I will look at different images of 1. Maybe one is like this, one is like that, one is like this. So if I look at all the images that are 1 and look how that pixel was for all those images, I'll get an idea, like if for an image that is 1, how likely this, how bright this pixel should be from the training data set, right? Because the training data set will tell you each image of 1 from the training data set will tell you how much bright this pixel was, how bright this pixel was, every pixel was. And we are assuming this pixel has nothing to do with this pixel. And that's why we can do this multiplication. Instead of computing the joint probability of all the 64 pixels, we'll just compute one probability for each pixel. We'll just multiply by that. So now can we estimate this from the training data set? Right? And we make an assumption that this probability actually falls follows a Gaussian distribution. And how do you characterize a Gaussian distribution? What do you need? What are the parameters of a Gaussian distribution?
Mean and variance.
Mean and variance, right? How many of you don't know what a Gaussian distribution is? How many of you know Gaussian distribution? What are the parameters? What do you need in order to characterize a Gaussian distribution? Yes.
Mean and where it's centered and the variation.
Right. So Gaussian distribution looks something like this. You have a mean, you have a variance. If all the values are exactly the same, then the Gaussian will look like a
Straight.
vertical line. There is no variance. But if it has a large variance, then the distribution will look something like this. So you need a mu, the mean, and you need to estimate the variance. So now, if I have many different images of one, the image of one character, then I could sample many different values of this pixel. And from those values, I could compute the mu and the variance. So I essentially estimated distribution over this pixel with that two parameters. And essentially, we're going to estimate distribution for each pixels from the training dataset. So that once our testing dataset comes, I could look at each pixel, and based on the distribution I learned, I can figure out how likely this pixel must have a value like this if y was actually a label 1. And what do we do about this?
Get rid of it.
What?
Get rid of it.
Get rid of it. We don't need to compute this. This is constant for all the 10 different classes. We don't compute this. Then you compute this probability for all the 10 classes, compare them, and assign the label that gets the maximum value. That is the most likely class. So essentially, by looking at a lot of images, and just imagine if it was one, most of the pixels around this column will actually lit up, right? But if it's a 6, like here, most of the time it will not lit up. So the distribution of these pixels for the pictures that is 6 will be centered around almost 0. The mean will be almost 0. But for 1, the mean will be around like 255, very bright. So you are learning different distribution for different type of words, and then if you are given a new word, let's say 5, and here you will not see a bright area, so you know for sure it is not 1. So you have a higher chance of rejecting 1, and maybe you have more competition between 5 or 6, which are somewhat closer. Sometimes as humans, we make mistakes, whether this is 5 or 6. I mean, rather than 1. It's the same thing for computer. Yes, question?
So this makes sense if they're doing like black and white data and there's a pixel value, like darkness of the pixel. How do they do color? Because
Good question. So in color, you basically have 3 different values, RGB, right? So each pixel, instead of one distribution, you learn 3 different distributions. That's it. And the other way is you just transform the colored image into grayscale image and apply this. Yes?
So would this work poorly if you had a larger space but the same size of characters? So if you were to like move the character over a little bit, it might get...
Yes. So these are called translation properties of images, right? And in order to, there are a wide range of challenges. This is the whole research field of computer vision, where maybe your sampled images were like mostly here, 1, 2, and the scaling problem and the alignment problem and all those things. there are dedicated algorithms to handle each of them, and there is a dedicated research community, thousands of people working every day overnight, publishing, submitting papers, getting rejected, and getting frustrated over this. Right? That's one field. My field is more related to text, so I do natural language understanding for my research. That's my bread and butter. But the underlying models are essentially the same. You will not find a dramatically different approach in learning. All it is trying to do is looking at the training data, try to estimate some distribution, how the data should look like, and then based on that distribution, when a new data point comes, you want to understand, does this distribution actually fit with this data? If it fits, then that's the right model. If it doesn't fit, it fits better with another distribution, so that is the right model. That's all this is doing. And that's where data science, AI, machine learning blends together. All right? How are we doing with time? Okay. Okay, so as I said, so for each pixel, right, this I here is now the pixel. And why now? You see this pixel is now a position, right? But I am not saying that's a problem now, because in text I said that's a problem. Why am I saying that? In text, we didn't like the position specific random variables. But now I'm just saying that's fine for images. Why?
Because of the pixel mapping.
Yes.
Because the distributions found are specific to the position of the pixels, so we need to consider the position of the pixels, like whatever the value is. But in text, it was not the same case with the position of the word in the entire document.
What about generality? Yes.
Didn't you say that you scale all the images to the exact same size in this data set?
Yes. So scaling an image, we make this assumption that it retains the property of the original image, while sampling of text may not.
You cannot scale in text.
Right? It might break the semantics, but the assumption we are making here is fine. It's just zoom in and zoom out kind of thing for images. That's fine. And it shouldn't make a much difference at the image level. For the document, it does. And that's why this xi, I is position specific, and that's fine. And we just want to know the distribution of each pixel based on a Gaussian distribution, right? So the parameters are essentially the sigma and the mu. That's what we need to know. Sigma is the variance, and mu is the mean, right? So mean and variance. That's all we need to know. And we can easily know by looking into the training data set, each pixel, their values, they get all those values, compute a mean, compute their variance. Simple. That essentially defines distribution of each pixel like this. And how do we estimate this? Whatever I have described here in terms of pixels, that's what you see here, the formulas. It's exactly, for example, this delta function is looking at a particular class. For example, whether it's a 1 or 2 or not. If it's a 1, for classes of 1, if it's a 1, look at the difference between the pixel value and the mean value, take their square, that is the variance. This is the classical definition. Okay? So just want to show one last example kind of thing. So let's say we want to classify. So this is an interesting experiment kind of thing, where there will be a person and they will be shown some images. And the images have got different kind of types, different types of images. For example, I take my word back. I said the wrong thing. We will make people read words. Okay? So the people might read a word that describes a tool or a building, or describes a person or an animal. What they did is, when I'm reading a particular word, they will scan the brain, take an image, and try to see if I read a dog, a word called dog, what happens to my brain versus, let's say, person, Donald Trump. What happens to my brain? Okay? And then looking at the image then, can I predict whether it was dog or the Trump? Okay? So that's kind of the experiment they did. So what they did is they created a training example. When they showed the word and took a lot of pictures of the brain. And what happened, so this is the setup, like 1 millimeter resolution, 2 images per second, whatever. This voxel is basically 3D pixels. And they had all this. But after that, for each different types, they computed kind of a mu. This is showing the mu of voxel for a particular word, type of word. So if you see, different type of word is creating different kind of, what is it called? Firing of the neurons. The images you see, like this one is just activating this part of the brain, but this type of word activates some other parts of the brain. And based on that, they can estimate a distribution for different type of words of the brain image for different pixels. Right? If I read animal kind of words, then how each of my pixel in my brain, if I take an image, actually fires. Those activations are being captured. So it's clear that different kind of words do different kind of activations in our brain. So we are basically imagining things, and that's how. And then when I have a new image like this, I can just look at, so it's basically reading your mind, right? So you can look at this, you can take an MRI picture of that person, and you can try to predict what is the word that the person is thinking. Right? So you essentially, for example, if you, between people word and animal word, both are kind of similar because both are living beings. But still there will be some difference that you may try to identify. For example, the blue part here is not that prominent, but here there is much more blue. Right? And you can try to read minds with that. And they showed that the pairwise classification accuracy they had was around 85%. Well, it may not be the right setup. Like it may be like very cherry-picked type of words with a small set of people, but that actually shows the power of AI. Quote unquote machine learning. Okay? So, what you should know, and I'm sure you don't know right now, at the end of this lecture, is what is an I-based classifier, what is the assumption it is making, why we use it, why such a dumb model, we still use that, how do we train it, how do we test it. And we have shown two cases, right? The discrete case and the continuous case. What was the discrete case?
Bag of words.
The text. What was the continuous case? The image. Yeah, so then we have this text classification, the discrete case, and for the Gaussian I-base, that was the continuous case, right? And the assignment that has been published is on text, right? You already probably are working with that. So any other questions? So how many of you have not yet signed up in a group, as a group for the project on Canvas? Because I still saw people last night. I have been emailing maybe at midnight yesterday, and I apologize for that. But have you all signed up to a particular group? Why not?
So I will today.
Yeah, please do, as soon as possible. Anything else? All right? Yeah, yeah.
I sent out that Teams link last night.
Yes.
But when I went to it, it was I had to request access. It wasn't the
I will approve it today. Yeah. I just opened the request, approved some, because instantly some people joined. So, but then there is a long queue I need to approve today. And please use that Teams link to ask questions, clarifications, because that's where I'm continuously logged in. So chances are higher that I will respond on Teams faster than on email or Canvas. So if you reach out with any concern to your classmates, to to your fellow project mates or even me or the TAs. Just post your message on Teams. You have a higher chance of getting a faster response. All right? Thank you very much.
ఇంకో
గ్రూప్ ఉందిరా నువ్వు నీ భయపడుతూ
యాడ్ అవ్వు ఇప్పుడే
ఇప్పుడే అవుతున్నా